Yay!
Yay! Hey, let's do a quick overview of the physics of capacitors, and in particular, this parallel plate capacitor setup. Like maybe I've got a battery that's 12 volts. Maybe I've got a couple pieces of metal that are 10 centimeters on a side. I'm going to separate them by 1 millimeter. So that's sort of exaggerated in the picture. The idea is that these plates are basically infinite. If you're in between the plates, 1 millimeter is pretty tiny compared to 10 centimeters. Well, it's like 1%, right? So essentially, if you're in the middle there, it looks like the plates are infinite sheets of charge. So just real quick, let's look at what that might look like. Let's see, I've been using green for positive, right? So what does the electric field look like coming off the top plate? Well, it's going above the plate, it's going up like that. And then it goes away from the positive plate, right? So in between, it looks something like this. And then below the bottom plate, it's still going away from the top plate, so it looks something like that. But we can do the same thing for the negative plate. For the negative plate, the electric field lines go in towards the negative plate, so we do that. Up here, they're going down towards the negative plate. And in here, in between, they're also going down towards the negative plate. So, I mean, look what happens. Above and below the capacitor, those electric fields cancel, right? So down here, E equals 0, and up here, E equals 0. And the idea is between the plates in here, the electric field is doubled. That's cool. It's uniform because remember, the field coming from an infinite sheet of charge is uniform. And in this case, it's twice as large as we would get from one sheet. So from one sheet, it would be sigma over 2 epsilon naught. Right? So the field between the plates is just sigma over epsilon naught. And remember what that is. Sigma was just our shorthand for charge per unit area. So it looks like that. Total charge on the plates divided by their area, and then that epsilon naught constant. Okay, so that's the electric field between the plates. Since we've separated positive and negative charges, there's a potential difference also. So we can write that down. Let's figure out what the potential difference is between the plates. I mean, I've already said it's 12 volts, right? But let's see if we can figure it out what it is in terms of the electric field. Remember, also we said that potential difference was minus E dot dl. Right? That was sort of a fundamental thing. So the electric field is pointed down. Let's take dl going that way, going from the bottom plate to the top plate. So those are our little steps. dl is a little step going from the bottom to the top. And what you notice is that that dot product, E dot dl, what is the, E dot dl is like E times dl times the cosine of the angle between the two. Well, the electric field is pointed down, dl is pointed up, so the angle between them is 180 degrees, right? And so the cosine of that is going to give you a minus sign. So this is just going to be a positive, that's going to cancel that minus sign, E times dl, and this is going from 0 up to, what did I call it? D is the final height. And the electric field is uniform, right? So that makes this extra easy to do. So this is just E times dl from 0 to d, but that's super easy to do. The integral of dl is just L evaluated from 0 to d. So what we get is the potential difference between the plates is also just the electric field times the separation of the plates, E times d. Okay, we can use all that stuff. All right, so now let's compute a number of things. Let's compute, I'll just call this part A. What is the capacitance? That's sort of the title of the whole thing. Capacitance is just defined as the amount of charge we store per volt All right, so the amount of charge we store per volt. Oh, look, I can get that in terms of the electric field because the electric field is Q over A epsilon naught, what we had found before. So this is just going to be, let's see, capacitance is just going to be E A epsilon naught, right? And then delta V between the plates is just E times D. Neat. So this is just going to be A epsilon naught over D. So that's the capacitance of the plates. Why we like this number is that, notice it doesn't depend on the battery. It doesn't depend on anything outside of the capacitor. It only depends on the geometry of the capacitor, its area. Epsilon naught, that's just a number. And then D, what the separation of the plates is. So it only depends on the geometry of the thing. So let's see what this would be. This would be, the area is, well, it's just 10 centimeters. That's 0.1 meters, right? And the area is just 0.1 squared. So the area is just 10 to the minus 2. And then epsilon naught, remember, is 8.85 times 10 to the minus 12th. And then some units that I'm not going to write down. And then D, that was 1 millimeter, right? 10 to the minus 3 in meters. Okay, so that's just going to give you 8.85 times 10 to the minus 11. So that's just going to be 88.5 picofarads, right? Pico is a 10 to the minus 12th. And a farad is, 1 farad is the unit of capacitance. Okay, so that's how we can compute the capacitance of a parallel plate. Just A epsilon naught over D. Pretty easy. Let's see, what else do we want to do? B. What is the amount of charge stored on the plates? We can calculate that. The amount of charge stored on the plate, well, that's just going to be the capacitance times the change in voltage. So that'd just be our 88.5 times 10 to the minus 12th times our 12 volts. And so if you do this, you get 1.06 nanocoulombs. All right, so that's the amount of charge we can actually store on the plates. What else can we do? C. What is the electric field between the plates? We went through all that trouble before. The electric field between the plates, there's a couple different ways you could do it. The electric field is sigma over epsilon naught, we said. So that's Q over A epsilon naught. And if you plug those numbers in, what did I get? 12,000. That's one way to do it. You could also get it this way. We said that the potential difference is E times D. So the other way I could do it is E is just the potential difference over D. And that you can almost do in your head, right? That's 12 divided by 1 millimeter, 10 to the minus 3. And so sure enough, you should get the same number, I hope, 12,000. Should be the same electric field. Okay, so just knowing some basic stuff, you can calculate the capacitance, the charge stored on the plates, the electric field between the plates. Here's one that'll become important. What about the energy stored? What is the energy stored in the plates? We know that there's energy stored because you can take this capacitor around somewhere else, connect the positive and negatives through like a light bulb or something and power the light bulb. So it's got to be storing energy somewhere. So how much energy is stored? Here's how you could look up the formula, but here's how you get it. The energy stored, what you have to do is you have to add up all the little bits of charge times the potential difference, right? Each little bit of charge is carried through this potential difference, and so that's a little bit of energy it takes to separate the charges. Okay, well, what is delta V? Delta V is just Q over C, so this is just going to be dQ Q over C, and this is from 0 all the way up to all the charge has been carried from one plate to the other. So that's just 1 over C Q dQ from 0 to Q. That's not the easiest integral in the world, but it's almost the easiest. So the integral of Q is just going to be 1/2c. It's just 1/2. Oops. Let's go ahead and stick. We already kind of know what the integral is going to be, so let's just stick a big Q. Let's put the limit in there. Q squared. But then C was Q over V, right? So this is just going to be, this is going to be 1/2. Q squared is C delta V. So let's put this in this, because often we know the C, right? The capacitance of the capacitor. And so this is just going to be our delta V squared. Okay, so that's going to be the energy stored in the capacitor. And if you just plug in your numbers, what did I get? 6.4 nanojoules. Not very much. This is a pretty small capacitor. 6.4 times 10 to the minus 9. And one more thing that we can get that will eventually be useful. There's the energy stored in the capacitor. Another measure that we might be interested in is called the energy density. And I really do mean density. I mean, in units, what I mean is joules per cubic meter. It's not obvious how this is useful yet. And by the way, that symbol is supposed to be a lowercase u. I don't know, on the board or on the iPad, I don't know how to make a lowercase u different from an uppercase u, so I sort of maybe have a little curl in there. This isn't terribly useful right now, but it will be eventually, so we might as well calculate it now. So per cubic meter, how much energy is stored? And the thinking behind this is that we're storing the energy in the electric field. That may not make a whole bunch of sense to you because the electric field is just imaginary arrows in space, right? But the idea is that we think, the view is that our model is that these arrows actually store energy. You can actually store energy in the vacuum. We'll expand more on that later, but so if that bothers you, that's fine. Maybe it should bother you. But we're going to say that we can store energy in the vacuum inside the electric field in these imaginary arrows, whatever that means. And so we can store a certain amount of joules per meter cubed in the electric field. So let's see what that's going to be. I already know how much energy I'm storing. It's just 1/2 C delta V squared, right? So this is going to be 1/2 C delta V squared, and I'm storing this in a certain amount of volume. And the volume is going to be what? A times D, right? A times D. That's the volume of this capacitor. Okay, so let's start plugging some stuff in. Let's simplify this just to get it in terms of the electric field. So this is going to be C. What is delta V? Delta V was ED, right? So this is just going to be E squared D squared over 2AD. It's still in the denominator. Let's see. Next, what can I do next? I know what the capacitance is. The capacitance is A epsilon naught over D. This is going to be 2AD squared. And this is still going to be E squared D squared on top, right? But now a bunch of stuff cancels out. D squared cancels out. The A cancels out. And so this energy density is just 1/2 epsilon naught E squared. When we finally talk about light and radiation, this is going to be really valuable for us, 1/2 epsilon naught E squared. So that's the energy density contained in the electric field. As it is now, we can just plug our numbers in, and what you're going to get is, what did I get? 640 microjoules per meter cubed. Okay, neat. So it doesn't have a lot of use right now, but that calculation is something that we're going to use quite a bit later, especially when we start talking about light. Okay, so there are some basics of capacitors. If you know the dimensions of a parallel plate capacitor, you can compute a whole bunch of stuff about it. The capacitance, the amount of charge stored, the potential difference between the plates, the electric field between the plates, the amount of energy stored, and so on. And so we'll use this quite a bit going forward.